Hi guys, good evening.
Sir, good evening, sir.
Good evening. Let's get started. I hope all of you are able to submit the assignment in time. I think there were few emails I met to reply to them. If you had emailed me with a small, correction or something, that is fine. I'll, inform the code office about that. Okay. Any other questions, anybody regarding assignment or anything else before we get started?
Sir, we are submitted, sir.
Submitted. Okay, okay. Sure, sure. Okay, sounds good. So let's get into the lecture. So we are dealing with this last topic in basics of finite difference method. That is the von Neumann stability analysis. Right. In this, we are dealing with the one-dimensional transient heat conduction equation. So we started off with partial u partial t equals alpha partial square by partial x square. And then what we said was in the von Neumann stability analysis, we're going to deal with the round of error, which is basically denoted using epsilon as u minus u tilde, where u is the solution that is obtained on a finite precision computer, and u tilde was the solution obtained on an infinite precision computer, right? So what we said was, of course, we would need to first discretize this continuous equation, and then we said the discretized equation for explicit Euler method look like ui n plus 1 minus ui n divided by delta t equals alpha by delta x square times ui plus 1 minus 2 times ui plus ui minus 1, all of them obtained at the time level n on the right-hand side. So then we said this is the discrete algebraic equation, or this is going to be the discrete algebraic equation set, right? Because we're going to apply the same equation at different points along the entire domain and for different times. So then we said if this particular equation is solved on a finite precision computer, then we are going to write this entire equation in terms of some function of u, capital U's. Similarly, if we're going to solve it on infinite precision computer, then we're going to obtain this equation for f of u tilde, right? That's what we said. And then we said we're going to substitute for u equals u tilde plus epsilon into the first equation. And then we have two equations. One is in terms of u tilde plus epsilon. The other one is in terms of u tilde. Then we said we're going to subtract off the u tilde equation from the u tilde plus epsilon equation, which is going to leave us with an equation which is going to leave us with a governing equation for a round of error, right, which was epsilon, right? Epsilon is in general a function of space and time. And then we said the governing equation for round of error is exactly the same as the governing equation for the primitive variable, that is u. Then we said we got this equation, which is exactly looking like the original governing equation that we have. Okay, then we have done several arguments. Now that we said, okay, solving for this equation directly with the initial conditions and boundary conditions doesn't make sense, because that is as complicated as solving the original equation. So if we set out to know whether this equation is going to be stable or not, then we are bombarded with this condition that you need to solve for this equation. Now, this equation is as complicated as solving this one. So as a result, we said we are not going to solve this in the conventional way. That means we're not going to start with initial condition, boundary condition, and then solve it. Rather, we said we're going to model the round of error, right? We're going to model the round of error. And in general, round of error has several frequencies. right? Several frequencies, and it is a very complicated function. And the round of error, another property that it has is that if there is some round of error, it will either grow or decay exponentially, right? So it means round of errors, if you observe in any simulation, they will quickly increase or they will quickly get damped. So that means this is an exponential in time behavior. So as a result, we said this round of error epsilon as a function of space and time can be modeled using an infinite Fourier series. We said e to the power amt, e to the power I k m x, going from where k was going from some minus n by 2 to plus n by 2, or 0 to n, something like that. So we said again, because the governing differential equation is linear, so as a result, we don't have to look at each and every term of this infinite series, or this series that is composed of several terms. We can look at a single term in this equation, a single term, and a single term behavior is good to analyze. Good to analyze because this is sufficient, right? This is going to basically tell us whether the resulting round of error, that is epsilon xt, is going to be stable or not. Okay, this we can do only because we have a linear algebraic equation here, the linear equation. If it is non-linear, then we cannot do this thing, because then you could have constructive interference or destructive interference, and two stable solutions in terms of round of error can add up to give you an unstable solution, or two unstable solutions can add up to give a stable solution, and so on. So as a result, we cannot apply this if you have non-linear governing equations. Rather, if you have a linear equation, we can just study the behavior with just a single term. This is also nice because solving it analytically is straightforward if you have to deal with only one term out of the equation rather than with all the terms that we have. Then we went ahead, we said, okay, we're going to just consider just a single term. We said epsilon m of xt, which is one mode or one component, which is going to be, we didn't write m on the right hand side anymore because we're dealing with one value. Then this is the mode that we have. Then we substituted for this into this equation with corresponding n plus 1, n I plus 1, I minus 1, and so on. And then eventually we obtained a condition. I think I made a small mistake in the last lecture. I should have written e to the power a delta t. Instead, I continued writing e to the power a t in towards the end of the lecture. So this is incorrect. This is correct. You may please, when you read it again, you correct it to e to the power a delta t. We said we are interested in what is the value of epsilon m at some spatial location at the next time step divided by round of error at the same spatial location at the current time step. And if this value is less than 1, then we said with a less than or equal to 1, then we said the method is going to be stable, right? Because the round of error at the next time step is less than or equal to the round of error that is at the previous time step. Then the method is stable. So this is the condition we identified. Of course, if you want to put in these values, then you can write this as e to the power a t plus delta t, right? Because we're dealing with t plus delta t times e to the power I k x divided by, now we are dealing with x and t. So this is going to be e to the power a t, e to the power I k x. Modulus of this is less than or equal to 1. This basically gives you, because e to the power a delta t, a t and I k x get cancelled in the numerator and denominator, leaves you with e to the power a delta t to be less than or equal to 1. So this value, we call it, we also represent with a letter called G, which is called the amplification factor. Okay, so this is the amplification factor. Okay, now if you substitute for epsilon I plus 1, I minus 1, all these things, and what we ended up in the last lecture was with e to the power a delta t equal to 1 minus 4r sine square theta by 2. I think somebody can correct me if this is incorrect. So where theta equals k times delta x. That is what we got. Okay, so this we got from the from this equation by substituting for epsilon m xt equals e to the power a t e to the power I k x. Okay, fine. Then what we want is, we want for this explicit Euler method, the amplification factor, which is the left hand side of this equation, to be less than 1, that is e power a delta t, to be less than or equal to 1. That means modulus of what we have on the right hand side is 1 minus 4r sine square theta by 2 to be less than or equal to 1. If I remove the modulus symbol, then we have basically this quantity, whatever is inside the modulus, should be between minus 1 to 1. So that means 1 minus 4r sine square theta by 2 should be between minus 1 and 1. Okay, then considering one condition at a time. So if I consider 1 minus 4r sine square theta by 2 to be less than or equal to 1, then what we have is 4r sine square theta by 2. If you bring it to the right hand side, is greater than or equal to 1 minus 1, that is 0. That means we are looking at this to be positive always. We know that 4 is always positive. Sine square theta by 2, the maximum value it can get is 1. Okay, that means r is greater than or equal to 0, which basically means that alpha delta t by delta x square is always positive. Always positive. So this is the condition we should satisfy. But then when we look at it, we know that alpha is already always positive. Delta t time step, we will always take it to be greater than 0. Delta x, the grid spacing, also will always be positive. So as a result, this condition is always satisfied. So as a result, choosing this less than or equal to 1 condition is not giving us any more restrictions on the delta t that we anticipated. So as a result, now we'll go ahead and look at the other limit, that is 1 minus 4r sine square theta by 2 to be greater than or equal to minus 1. So I will choose minus 1 less than or equal to 1 minus 4r sine square theta by 2, which basically gives me 4r sine square theta by 2 to be less than or equal to 2. And because we are looking at this entire quantity to be the minimum, we will substitute for the maximum value of this. This is going to be maximum value is going to be plus 1 for sine square theta by 2. So as a result, r should be less than or equal to 1 by 2. But we know that r is nothing but alpha delta t by delta x square should be less than or equal to 1 by 2. That means our delta t should be less than or equal to delta x square by 2 alpha. Okay, so that is the restriction on the time step. That we are given if we have to use the explicit Euler method. Okay, that means if you want to solve this one-dimensional transient heat conduction equation with explicit Euler method, then we cannot choose. So once you fix your delta x, and once you know the thermal diffusivity, which is fixed for a particular problem, depending on the domain you are considering, depending on the material you are considering, then delta x square and alpha are already fixed. Okay, then delta x square by 2 alpha is your maximum time step you can take. That means you cannot take any arbitrary time step. It should be less than or equal to this value. Okay, many a times this can come out to be very small because delta x is already small, and then square of that is even more smaller, and then your alpha and 2 will further divide that thing, and then as a result delta t will come out to be kind of small. Okay, so delta t will become quite small and restrictive in general in some cases. So we need to be kind of respect that and then only take that delta t. If we take any delta t greater than this thing, what will happen? Essentially, your round of errors will grow, and then your solution will eventually become not a number. It will become very large, and we're not able to get an answer. So we should keep in mind that there is a restriction on the time step for delta t whenever we use an explicit method. Now, this will become handy when you try to solve some problems, let's say in solid mechanics or fluid mechanics with in CFD or FEA with some of these softwares. The software might tell you that you cannot choose any delta t you want, but then in general, when you're dealing with any explicit time stepping schemes, there is always some delta t restriction that is applied. So you have to accordingly choose your delta t, otherwise your solution will just diverge, and the reason will be because you have chosen a very large delta t, which you should not have because you're dealing with explicit schemes. Okay, fine. Now, so far so good. Of course, now you may wonder that now can this, okay, we are dealing with the one-dimensional equation. Now, of course, you can also extend this to 2 dimensions. Okay, by putting in instead of this, you can also write alpha times dou square u by dou x square plus dou square u by dou y square. And then, of course, you have to make some assumptions in terms of how your kmx and kmy can vary and so on. If you do that, essentially what you'll see is that you'll get a different quantity with certain assumptions, that in the denominator, instead of 2 alpha, you're going to maybe get 4 alpha or something, because you have now delta x square by 2 alpha plus delta y square by 2 alpha, something like that, which is basically, will give you probably a larger value in the denominator that you have to see. Okay, so yeah, so essentially your time step restriction will basically become maybe even more. I think that you have to figure it out by substituting these values. Okay. Anyway, then let us look at the other method, which is the so that means before I conclude, so explicit Euler method by the solution of von Neumann stability analysis is only conditionally stable. Okay, that means we cannot. It is a stable method conditionally. That means as long as you satisfy the condition delta t less than or equal to delta x square by 2 alpha, then it is going to be stable. Okay, it's going to give you an answer. Okay, so we call such a method as conditionally stable. Fine. Let us look at, but then implementing the method is straightforward because there is nothing you have to do. Only thing is that everything on the right hand side needs to be just calculated by substitution, right? You just need to substitute and calculate. So as far as the implementation is concerned, it is the easiest, right? Because you just have to, everything on the right hand side. You need to calculate what is ui n plus 1. That's all. So that means send everything to right hand side, substitute all the known values at n, and then calculate the values at n plus 1. Okay. Fine. Let's move on to the other method, that is the implicit Euler method. Okay. So in the implicit Euler method, we know that when we discretize the 1D transient heat conduction equation, that is dou u by dou t equals alpha dou square u by dou x square, we discretize it as ui n plus 1 minus ui n divided by delta t equals alpha times ui plus 1 minus 2 ui plus ui minus 1, and all of them divided by delta x square, all of them at n plus 1 instead of at n. That means everything on the right hand side is unknown, right? These are all required at n plus 1 stage rather than at n time level. So that means we don't know any of these things. But we know that to solve this, essentially we said we have to basically form a system of equations, right? Because you send everything at n plus 1 to the left hand side, then you form a system of equations, and because you're dealing with I plus 1, I and I minus 1, you're essentially going to end up with a tridiagonal matrix system, and then you would use TDMA to solve it at every time step, right? That means whatever the TDMA algorithm you have, you're going to call that function at every time step to get what is your U distribution for I going from 0 to capital N, okay, essentially all the values. Okay, so this is, as you can see, this is already expensive because earlier you were not calling any TDMA matrix routines. You are just substituting and calculating. That is like a one line. But here you are calling for TDMA, which is I think phi n minus 1 plus 4 times the is the operation count. So you are doing more computations. But then what is the advantage you are getting with this method? Okay, so that is what we are going to see by looking at the stability of the implicit Euler method. We know that we are already putting in more computational effort in solving this equation using the implicit Euler method. Okay, so then we follow pretty much the same steps in the von Neumann stability analysis. So that means we're going to write this discrete equation in terms of capital U. Then we're going to write it in terms of U tilde. Then we're going to use the round of error equals U minus U tilde, and then going to substitute U equals U tilde plus epsilon. In this equation, we're going to write it as U tilde plus epsilon, and then going to subtract this equation. From this equation, we're going to subtract the equation for U tilde. That's going to give you a governing equation for error as epsilon I n plus 1 minus epsilon I n divided by delta t equals alpha by delta x square, epsilon I plus 1 minus 2 times epsilon I plus epsilon I minus 1, all of them at n plus 1. Okay, so that's what you're going to get. So this is exactly like the governing equation. Only thing is that now we replaced u with epsilon. Okay, so this is the governing equation for the round of error. Okay, now again we make the same assumption about how round of error is going to behave and so on, and then eventually going to substitute for epsilon m of xt equals e to the at times e to the ikx. That means we have in general an exponentially decaying or growing solution in time, and then we say whatever is the function that we have for round of error, that can be represented using an infinite sum of sines and cosines as in a Fourier series, and then we are dealing with only one term of this series. Okay, because that is sufficient to tell us, because this equation is linear, that is sufficient to tell us whether the system is going to be stable or not, under what conditions it is going to be stable. Now, okay, in the exams or in the assignments, I think it is a good idea to quickly write these equations, okay, and then arrive at this equation. Although I have directly written that equation from here, I think for your, or you can even say these things in writing, and then you can directly write this equation. Okay, so I think I leave it up to you how you want to analyze these problems, okay, in the exams or in the assignments. But eventually you have to at least show the round of error equation, and then you can again show how you model the round of error, just like what we have done here. So that is kind of straightforward. Then I'm going to evaluate what is EMX at these values. Okay, so what will be epsilon I n plus 1? This is going to be e to the power a. N plus 1 is, okay, let me write one more thing here. So this is going to be epsilon at x comma t plus delta t. That means we're dealing with x and t plus delta t. So this is going to be e to the power a t, e to the power a times t plus delta t times e to the power I k x. And what I want is epsilon I n. This is nothing but epsilon at x comma t. This is e to the power a t times e to the power I k x. Then we need to calculate epsilon I plus 1, epsilon I minus 1. This we already have calculated here. So we just need to calculate epsilon I plus 1 and epsilon I minus 1 at the time level n plus 1. Okay, that means epsilon I plus 1 at n plus 1 is going to be epsilon at x plus delta x, comma t plus delta t. That is going to be e to the power a t plus delta t times e to the power I k x plus delta x. Similarly, epsilon I minus 1 at n plus 1 is going to be epsilon x minus delta x t plus dt. That is going to be e to the power a t plus dt e to the power I k x minus delta x. Okay. All right. So then we have all the four quantities available. So we can actually just substitute them in this equation and then see what we're going to get. So on the left hand side, we have epsilon I n plus 1, that is going to be e to the power a t plus delta t e to the power I k x minus e to the power epsilon I n is going to be e to the power a t e to the power I k x divided by delta t equals alpha by delta x square. Epsilon I plus 1 n plus 1 is going to be e to the power a t plus delta t e to the power I k x plus delta x minus e to the power a t e to the power I k x. That is for epsilon I n plus 1. So this is going to be, sorry, so we're going to be a t plus delta t. And then we have plus epsilon, oh, there is a 2 here, right? There is 2 here, right? This is minus 2 epsilon I, okay? And then we have plus epsilon I minus 1 and plus 1, that's going to be e to the power a t plus delta t e to the power I k x minus delta x. So I can write this as, e to the power a t times e to the power I k x common. This is going to give me e to the power a delta t minus 1 equals alpha delta t by delta x square times, again I can take e to the power a t plus delta t common from all of them, okay, and then e to the power I k x common. So that's going to give me e to the power I k delta x minus 2 plus e to the power minus I k delta x times e to the power a t times e to the power a delta t times e to the power I k x, right? Let me write it below, times e to the power I k x, okay? And that's what we have. Okay, then e to the power at, e to the power ikx, e to the power at, e to the power ikx gets cancelled on both sides. And what we have is e to the a delta t minus 1 equals, let's call this as some factor r, just like before, r times e to the power ik delta x plus e to the power minus ik delta x minus 2 times e to the power a delta t. We have seen earlier that e to the power I theta plus e to the power minus I theta is nothing but 2 times cosine theta, and 2 times cosine theta is nothing but 2 times, okay, so this is 2 times cosine theta, and then if we consider your theta equals k delta x, we can write this as e to the power a delta t minus 1 equals r times 2 times cosine theta minus 2 times e to the power a delta t, okay? So this is nothing but 2r times cos theta can be written as 1 minus 2 sine square theta by 2, and then this 2 is gone out, so it becomes 1, and then you put e to the power a delta t, so a delta t minus 1. Okay, so then what we have is the 1 gets cancelled. Then what we have is we can simplify these things. So it's going to be e to the power a delta t times 1. Okay, so that is taking out this common. This is also a component of multiplication of e to the power a delta t, but there is a minus 2 sine square theta by 2 by times 2r. There's going to be minus 4r sine square theta by 2. If it comes to left hand side, it will become plus 4r sine square theta by 2 equals 1. Okay, e to the power a delta t equals 1 upon 1 plus 4r sine square theta by 2. Okay, that is the condition we got. Okay, so in most of the cases, any problems any analysis problems you want to solve, coming up to here is kind of very straightforward. So that part you should be able to do it as much correctly as possible. Now from here is where you have to think a little bit and see under what conditions will this be stable or not. Okay, that is where several of these schemes can differ. Okay, as we have seen before, we identified when modulus of something was less than or equal to 1, we said this is going to be minus 1 less than or equal to this value less than or equal to 1, and then we equated it to minus 1 and plus 1 and then solved it. Similarly here we're going to do that. So this is the amplification factor which we have seen. So we want e power delta t to be less than or equal to 1 for the method to be stable. Okay, that means I'm going to consider this right hand side, that is 1 by 1 plus 4r sine square theta by 2 modulus of the to be less than or equal to 1. Okay, we know that 4 is always positive. Sine square by theta by 2 is also always positive, right? R is always positive because R equals alpha delta t by delta x square. This is always a positive quantity. Okay, so as a result, this entire thing is greater than 0, right? This is always positive. What would be 1 by 1 plus some positive quantity? This will always be less than or equal to 1, right? Because you're dividing 1 with a quantity that is larger than 1 and positive. So as a result, this will always be less than or equal to 1. Okay, so that means this is always satisfied irrespective of what alpha, what delta t, what delta x you're going to choose. Okay, this is always satisfied. That means the implicit Euler method is unconditionally stable, right? Because there is no condition that the method, the von Neumann stability analysis puts on the method for it to be stable. Okay, that means it is unconditionally stable. That means we can take delta t to be as large as possible. Okay, but this is not quite right, because although we can take delta t to be as large as possible, stability doesn't mean accuracy. Okay, that means from the stability point of view, we can take delta t to be as large as possible, but that doesn't mean that the solution is going to be accurate. Okay, so you need to still take delta t to be as small as possible, as small, such that we're going to get an accurate solution. Okay, what does it mean? This means that stability tells you that even if you take larger delta t, you're going to still get an answer. Okay, that means you're going to get a bounded value as your answer, but that answer may not be accurate. Okay, so that means we are still restricted by accuracy we want in choosing delta t, but delta t can in general be larger than the delta t you have chosen in the explicit Euler method. That means the delta t you have chosen in the, or you will choose in the implicit Euler method, can be in general will be greater than the delta t that you had used in the explicit method. Okay, so as a result, you can take a larger delta t. A larger delta t means that you can arrive at the final time in fewer number of steps, right? So that is the benefit you are getting, but you cannot take it very large. That means, for example, if let's say delta t explicit you had used 1 into 10 power minus 3, perhaps delta t in the implicit method you could choose at 10 power minus 2. But let us say if you still have to simulate for 5 seconds, you can't choose delta t to be, let us say, 1 second, because with 1 second you may still get an answer, but the answer will be grossly incorrect. Okay, because you just want to do 5 steps and then get an answer, it is not possible. Okay, so we are still restricted by the accuracy that we want in choosing delta t, but implicit method tells you that you can choose. There is no stability condition that it imposes. Okay, that means the extra computational effort we are putting by solving this tridiagonal matrix algorithm is justified through the use of a larger delta t in the implicit Euler case. Okay, so you might have again seen when you use some of these software, you are presented with an implicit method, then in general you can choose a slightly larger delta t. Okay, probably an order of magnitude higher or twice or thrice of the previous delta t that you have chosen. If you're chosen in the context of an explicit method. Okay, so that is the idea here. Any questions so far, anybody? Okay, so then let's move on. So we have one more discretization that we have seen earlier, that is known as the Crank-Nicolson method. Crank-Nicolson method. Okay, what do we do in this method? Essentially, we said the equation is evaluated at time t equals n plus half. Okay, so everything is evaluated n plus half. So as a result, we wrote the discretization for our 1D transient diffusion equation as ui n plus 1 minus ui n divided by delta t equals alpha by delta x square. On the right hand side, we said this is going to be ui plus 1 minus 2 ui plus ui minus 1, all of them at time level n, plus you have ui plus 1 minus 2 ui plus ui minus 1 at time level n plus 1, and then average of this two, so it's going to be 1/2, right? So that's what we said. And then again, this is basically something like a central scheme about n plus half. That means you're going delta t by 2 to the positive side and delta t by 2 to the negative side. Okay, so this is your governing differential equation for the temperature. Okay, now again, we have also showed that this method is actually order delta x square, order delta t square, right, earlier in the context of calculating the truncation error, right? So you remember we have done this delta x square, delta t square, whereas the implicit Euler method and the explicit Euler methods were only order delta x, order delta t. Okay, I think if you remember correctly. Okay, fine. So so that's why we kind of prefer this Crank-Nicolson method, because it is second order both in space and time. Okay, fine. So So now what we have is, okay, now we have to do the same analysis. That is, we have to see, is this method going to be stable or not? Okay. So for that, excuse me, we're going to apply the von Neumann stability analysis. Okay. So again, we follow the same steps as we have done before. That means we're going to write an equation, discretize this using U, then discretize this using U tilde. Then we're going to come up with an equation for the round off error, that is epsilon, by substituting for U in terms of U tilde and epsilon, and then going to subtract one equation from the other. Then our governing equation for round off error will come out to be exactly same as the governing equation, where U is replaced with epsilon. So this is going to be epsilon I n plus 1 minus epsilon I n divided by delta t equals alpha by 2 times delta x square, epsilon I plus 1 minus 2 epsilon I plus epsilon I minus 1 evaluated at n, plus epsilon I plus 1 minus 2 times epsilon I plus epsilon I minus 1 evaluated at n plus 1. Okay, so that's what we have. Fine. So then again, we're going to call upon the Fourier series and then going to write we're going to write the entire series and then say that one of the terms is sufficient to model this thing. So we're going to write epsilon mxt equals e to the power at e to the power ikx. Then we would need these quantities, that is epsilon I n plus 1 equals epsilon of x comma t plus delta t. That is going to be e to the power a times t plus delta t e to the power ikx. Then we will need epsilon I n equals epsilon of xt. That's going to be e to the power at e to the power ikx. Then we would need epsilon I plus 1 at n. This is x plus delta x comma t. This is going to be e to the power at e to the power ikx plus delta x. Then epsilon I minus 1 at equals x minus delta x comma t. This is going to be e to the power at e to the power ikx minus delta x. Then we would need epsilon I plus 1 and plus 1 equals epsilon x plus delta x t plus delta t is going to be e to the power a t plus delta t e to the power ik x plus delta x. Then finally we need epsilon I minus 1 and plus 1 equals epsilon x minus delta x t plus delta t, going to be e to the power a t plus delta t e to the power ik x minus delta x. Okay, so we have all these things. So we need to go back and substitute in this. So I think this we have done earlier. So I'll just do it again. So this is going to be on the left hand side. If you do this, we're going to essentially get e to the power a delta t minus 1 equals r times. You remember, so this is going to be not r, this is going to be r by 2, right? We have, if you define alpha delta t by delta x square as r. So then we're going to get basically e to the power a t e to the power ikx cancelled on both sides. So this will turn out to be essentially as before. This is going to be 2 times or this will turn out to be how much? Okay, let me substitute and do it. Maybe that's easier. So this will turn out to be e to the power. Okay, this will turn out to be e to the power ik delta x plus e to the power minus ik delta x minus 2. And the other one will turn out to be also e to the power ik delta x plus e to the power minus ik delta x minus 2. But then it will have multiplication with e to the power a delta t, right? Because everything is now at n plus 1, right? So that is the only change you will have. Now, if you take k delta x to be equal to theta, we're going to get this as, we're going to get the first term as 2 cosine theta minus 2. That means 2 times 1 minus 2 sine square theta by 2 minus 1 minus 1. This is going to give you minus 4 sine square theta by 2. Okay. So this also will give you minus 4 sine square theta by 2, but then with a multiplication with e power a delta t. So if you write here e power a delta t minus 1 equals r by 2 times, we're going to get minus 4r sine square theta by 2 minus 4r sine square theta by 2 times e to the power a delta t. Okay, that's what we get. So let us combine the terms of e to the power a delta t to the left hand side. So e to the power a delta t, not at, e to the power a delta t times 1 plus, oh, yeah, so there is no r here. Right now I have substituted for r here. So this is going to be, this r is essentially gone inside. Okay, and then there is a 1/2 here. Okay, so let's say 1/2. So this is going to be 1 plus 2r sine square theta by 2 equals 1 minus 2r sine square theta by 2. That means e to the power a delta t equals 1 minus 2r sine square theta by 2 divided by 1 plus 2r sine square theta by 2. Okay. Okay, so the maximum value, so we want modulus of this to be less than or equal to 1. We know that the maximum value for sine square theta by 2 is 1 and r is always positive, 2 is always positive. So this quantity is essentially is going to be this is always satisfied, right? You have 1 minus 2r sine square theta by 2 by 1 plus 2r sine square theta by 2. Let us say if this quantity is less than 1, if this quantity is less than 1, this is already always less than 1, right? Because you have 1 minus something less than 1 divided by 1 plus something less than 1. That is always satisfied. Even if you have this quantity is greater than 1, then what you have is you have minus 2r sine square theta by 2 is going to be smaller than this one, right? Because you have 1 minus this thing and 1 plus this thing. So this condition is again always satisfied, right? This is always satisfied. So as a result, the Crank-Nicolson method is also unconditionally stable method. Okay, so there is no restriction on the delta t. You can choose again as delta t can be as large as possible, but only restricted by accuracy. So how do we know whether the delta t is going to be, a particular delta t we chosen is going to be accurate or not? We would not know. We have to take it and then do it and then see if there is a reference data we can compare. Otherwise, we have to choose. We cannot choose really large delta t values. Okay, that is the only way. So that's why we have something called independence of the solution from the delta x and delta t values that you choose. That means once you solve for it, you should choose different delta x values and different delta t values and show that your solution is not changing with respect to different delta x and different delta t you have chosen. Okay, we call such a solution as independent solution, or essentially this is kind of a grid and time step independent solution. That means your solution is not dependent on the delta x and delta t you have chosen. Okay, so that is the idea. Okay, now one more question that brings up here is that then if both the implicit Euler and the Crank-Nicolson methods are unstable, unconditionally stable, sorry, if both implicit Euler and Crank-Nicolson method are unconditionally stable, that is, they are always stable, then which method should I use? Then which method should one use? Well, it turns out if you want to solve your system using implicit Euler, you have to solve for a TDMA, right? So if you go back to this equation, you see that this left-hand side is pretty much the same as in the implicit Euler case. This right-hand side, this was there in the implicit Euler case. So the only new thing here was addition of this quantity and then this 1/2. That means if you have to solve, if you have set up your matrix for implicit Euler, right, to solve using TDMA. By the way, solution of Crank-Nicolson also requires TDMA because you have n+1. Now, if you want to modify an existing implicit Euler code to to Crank-Nicolson method, then the only change you need to do is that you need to multiply that code with this right-hand side with this 1/2, okay, appropriately. And then in the B term, when you write AX equal to B, in the B term, you need to add extra this UI plus 1 minus 2i plus UI minus 1 at the nth time level. That's all, right? Because this will go into the TDMA on the left-hand side. So that is the only change you have to make if you want to convert your existing code, which is written on implicit Euler, to a Crank-Nicolson. And we realize that both methods are unconditionally stable. So both of them are going to work with the same delta t. But then what is the advantage? The advantage is that with just the addition of this extra thing on the right-hand side and this introduction of alpha, we're going to bump up our accuracy to delta t square, delta x square without much increase in additional computational cost. Instead of just working with order delta t, delta x in the case of implicit Euler. Okay, so wherever possible, we should try to use the Crank-Nicolson method in place of implicit Euler, because you are essentially getting second order accuracy both in space and time at pretty much not much extra cost. Okay, so that's why we should always prefer. So we prefer Crank-Nicolson method to implicit Euler, because with a small additional with a small addition in computation cost, or a small increase in computational cost, we can get order t square, order delta x square solution instead of just order delta t, order delta x in the case of implicit Euler method. Okay. Okay, so that is the entire concept. So with this, we finish the stability analysis, and that finishes the basics of the finite difference method. Okay. So that finishes basics of the finite. So that means we finished the 3 chapters. That is the solution to system of linear equations, solution to system of nonlinear equations, and then the basics of the finite difference method. Okay. So however, for midterm exam, we're only going to have the first 2 chapters. Okay, that is the solution to system of linear equations and solution to system of nonlinear equations. Only these 2 chapters we'll have for the midterm, and for the end exam, of course, you'll have all the chapters in there. Okay, so that basically finishes the chapter on basics of finite difference method. Any questions before we start the next chapter, that is on solution to ordinary differential equations? Any questions so far? Questions?
Sir, good evening, sir.
Hi, good evening. Yeah.
Sir, am I audible, sir?
Audible. Yes, yes. Please go ahead.
Yes, sir. My question is like I wanted to solve some, say, sample problems on the 2 chapters, whatever you have taught us, sir. So where may we find some good examples that we may take reference from, sir?
Yeah. So definitely you can pick up this book. I think in the syllabus, did I post the syllabus? In the syllabus we have this thing, I think, numerical methods by Chinne and Kincaid. Okay. That is a good book. You can pick up that one, or you can even pick up numerical methods by Parviz Moin. Okay. So this is somewhat easier because there are some there is several, lot of description, lot of example problems and all. So you might find it, and then there are also several numerical problems in the exercises. Parviz Moin's book is kind of a short book, but this has a few examples are there, but then the problems are maybe on the tougher side, you may find. But it's okay. You can pick up any of these books. I think these are better, for the preparation point of view.
Okay. Thank you so much.
There is
sir.
also a book by Atkinson, but Atkinson's book is, I mean, I taught some theory from Atkinson. This is numerical analysis or something. But Atkinson's book is more from mathematics point of view, rather than from numerical point of view. So it also has some examples. Yeah, you can either, pick up this book. But Chennai and Kenkai might be the better, first one you would choose. Yeah.
Okay. Thank you, sir.
Thank you. Let's have these books somewhere. Yeah. Any other questions, anybody?
Sir, Arunachal here.
Yeah.
Sir, for midterm, we are allowed to take one formula sheet.
Yeah, I think I will probably keep it open notes. I think that is okay.
Sir, open notes.
They may not allow or something.
No, sir. Open notes. We thought that it is closed book is enough for us.
Oh, I see. Closed book will be somewhat easier, isn't it?
Yes, that is what. Even
Yeah,
like
I think I would prefer that way. I don't think it will be a problem. You can write, whatever you want on, one sheet or two sheets, not a problem.
Okay, sir.
I think that is better because that. Yeah, go
Sorry
ahead.
to interrupt, sir. Yeah. So from our batch, like we are able to get the feedback from the students.
Yeah.
But I would also discuss with Arunachalam, our senior batch representative.
Sure. Yeah, you decide and tell me whether you wanted open notes or closed notes. Both are fine with me. But if it is closed notes, you can bring one sheet of paper or two sheets of paper with whatever formulas you want to write and everything.
Right, sir.
That's
Okay,
not a
sir.
problem. I would, if I were a student, I would prefer, getting a sheet with written, with all the equations written, because that way I'm also doing some preparation for the exam.
Correct, sir.
If it is open notes, the tendency is that usually students start reading the notes in the exam. So,
We don't want, sir.
which is not a good idea. So I think it's better if you do come with a cheat sheet, one sheet or two sheets. It's up to you. I can, increase that, where you write whatever you want. And that way you are also less distracted, instead of flipping the pages in the exam for all the 60, 70 pages that you may write.
Right, sir.
Yeah.
Sir, our
You decide
batch-
and tell me. Okay, go ahead. Yeah.
Yes. Yeah, from our batch, it is very clear. We will go with closed book with
Yeah.
one or two sheets as a formula sheet, sir.
Sure.
Children
Yeah.
may confirm on tomorrow, sir.
Yeah, sure. No problem.
Thank you,
When
sir.
is the exam? Exam is on 7th of November. Huh?
Sir, 16th.
November 16th, sir.
Oh, November 16th. Okay. So we have quite a lot of time.
Yes, sir. Yes.
It's actually almost towards the fag end of the course, isn't it?
Correct, sir.
Spectrum. Yeah.
Yes.
Okay. Yeah, we'll keep it maybe, this will be online exam, right? So you will write it and then scan it and, upload it to the drive or something.
Right, sir.
Okay. So then we will probably keep it maybe 1 hour, 15 minutes or something like that for the exam.
1:30, 1 hour, 30 minutes.
1 hour 30. Okay. So we'll keep it 1 hour, 30 minutes, and then final exam will be 3 hours maybe.
Yes, sir. Yes, sir.
Okay, fine. So we'll stick to 1.5 hours and then final exam 3 hours. That should be good.
So just a question here, sir. So
Sure.
I know like the numerical analysis, this will be like even for solving it will take more time. So do you think like within 1.5 hour will be sufficient for the exam?
Yeah, you should be able to solve. Yeah, I'll probably give only maybe 2 questions or maximum 3 questions, not even 3.
Okay, sir.
You should be able to solve it. So you should be able to solve it and scan it and verify and then upload everything within 1.5 hours.
Okay, sure, sir.
Should not be a problem. I'll set the question paper so that you can solve it in let's say about 1 hour or something. 1 hour 10 minutes. So you'll have some 20 minutes to reevaluate your answers before you submit.
Sure, sir.
Hello, sir.
Yeah, hi.
Hello, sir. It's Amit again.
Yeah.
Sir, actually, during the quiz for the other subject, some of our classmates faced issues with just getting access to the portal, or due to like other technical issues, they were not able to begin the test itself on time. So maybe is it possible that the code can support us with extension of time if such an event occurs? Because they were not entirely sure as to how they can help us the last time around.
Okay, so
Maybe Chidambaram or someone can add on that.
Amit, we have to connect with the code office only before starting the exam.
Okay, Arunachalam, sir. Okay.
Yeah. So what I feel is that, see, essentially it will be a question paper with just a PDF. That's all. I think in case if somebody is not able to access something like that, maybe code office can email the PDF or something like that, because it's not going to be multiple choice or anything. You will basically derive things, or work on the values and then scan it and upload. So I don't think it's not a, computer based exam.
It's a pending action from my side, like based on the discussion with Shankar sir. Okay, last time the students faced, I think, like for initial setting up time, like in the sense verification, it took some time actually.
Oh,
yeah, so because 20 people were there, and it took like more than like half an hour actually. So that was a concern.
Oh, verification meaning the ID card or something like that, is it? Oh, I see. Okay. No, I think in that case, they will definitely give you time. I don't think it should be a problem.
Yes, sir. Yes. Sir.
Yeah.
I would also bring that concern with the code office, and we would.
Yeah. Sure. In fact, what I feel is that, they can send you the question paper and you can start writing. Whenever your turn comes, you can show your ID card. That is probably better. But again, understand.
No, sir. They have to verify it, and only then it will allow us to access the question paper, sir. It's
I
kind of
see.
set up in that way.
Okay. No, I think maybe
we'll like individually call our names out and then verify our identities.
Oh, I see. Okay. No, I hope they do it, in a different way, so that you're not going to be delayed, at the start. Can one of you check with the code office so that?
Amit, sir, sorry to interrupt. Whatever the delay happens, the code office people will allow whatever the 5 minutes delay, they allow that extend the 5 minutes in the post to exam. So that will be compensated. Don't worry about that. That is what happened last time also with our batch. If the exam starts at 10 o'clock, if we are not able to join at 10 o'clock. If we start with 10:05, then they allow to write up to 11:35 because of the technical issues.
Sure. So last time, like we, like I think some of us started 15 minutes late, and I think like
whatever the delay happens because of technical issue, code office compensated the whatever the delay in the end of the exam.
Yeah, and they did compensate it, but I think there were some interruptions. It was got off, and then they reassigned it. So
we will discuss with the code office post to this class.
Yes, sure.
Thank you, sir.
Okay, all right.
Sure, thank you, sir.
Okay, any other questions, anybody?
That's it then. Thank you.
So, okay.
Thank you, sir.
Fine.
Thank you, sir.
Fine then. All right. Thank you. Talk to you guys tomorrow at 4 o'clock. Okay.
Thank you, sir.
Bye. Thank you.
Thank you, sir.
Thank you.
Thank you, Professor, sir.